I'm going to call this video exponential rates. The rate that we're given, the derivative, is actually not going to have an exponential part to it, but when we work backwards from that and find the original equation, that is going to be exponential. So I think the term here is a little misleading, but it's related to rates, which we're currently talking about, and when we work backwards we get this exponential idea. So what we're going to focus on is anything that is phrased this way. When they say the rate of y to x is proportional to y. And when we think of that in math language, we're going to say the derivative is going to be equal to a number times y. That's what they mean when they say proportional to y. So we're going to try and work backwards and solve something related to this. We're going to start by just using the variables that are here and just kind of thinking about what this would entail. So if I want to basically take the antiderivative, I can't do that when I have a y on the right side. So I need to separate the variables. So it goes back to our last unit and we need to do separation of variables. So I'm going to divide both sides by y and bring the dx over to the right side. So I would have 1 over y with a dy, and that equals k times dx. And then I'm going to add the symbolism onto either side. That means take an antiderivative. So on the left side, the antiderivative of 1 over y is the natural log of y, and really it's the absolute value of the natural log of the absolute value of y. On the right side, remember k is just a number. So what would you do if you had to take the antiderivative of 2 or of 4 or of 6? What would you have to take the derivative of to get those numbers? And so in the end, we just end up adding an x there, an x to the end of it, right? So the derivative of kx would just be k. The derivative of 2x is just 2. The derivative of 4x is just 4. So that's why we work it that way, and then we always add the plus c at the end. I want to solve for y. So one thing that I'm going to do is to get just y closer to itself, I'm going to make e the base of everything on the left side. Because when I do that, the e and the natural log will cancel off. And so I'm going to do the same thing on the right side. E becomes the base of that entire thing. So on the left side, e and natural log cancel off, so I have absolute value of y left behind. And on the right side, I'm going to apply some of our power rules, and I could actually rewrite that as e to the kx times e to the c. So if I'm adding the powers, I can actually separate them and just have them go to the individual base, but then I multiply them together. So we can just refresh you on that before or at class tomorrow if we need to. From there, I need to think about how do I get rid of that absolute value symbol. How can I get that out of there so that the y is totally by itself? Well, if I go back to what's on the right side, I'm just going to swing up here a second. One thing I'm going to do is just rewrite this a second and switch the parts around that were on the right side. So I'll do something like that. Okay, so when I am thinking of absolute value, if I want to get rid of that, what really happens is that means the thing on the right side could be positive or negative. And what you'll see is that positive or negative symbol will kind of work its way out of the equation when I look at what we have on top here. So let's just consider that when x is 0, y is going to equal y sub 0. We're just going to say that's the initial value. So let's go ahead and just see what would happen. I'll use a different color for a little bit just so we kind of realize we're plugging some stuff in. So if on the right side, if I'm going to plug in a 0 for x, what we're saying is the y value is y sub 0. Okay, so when I do that, the next line here, this won't change at all, but the e to the k times 0 power, that ends up being just e to the 0 power, that whole thing just gets a 1. So it doesn't really matter in this part, and what we figure out is that this whole chunk is going to equal the initial value. That's always going to happen. We're using some symbolism here, but that will always happen. This first chunk here will always be the initial value. Whenever x is 0, that initial chunk has to be the initial value. So, we just kind of skip through here. What we've learned is that now my overall equation is going to be this. Whenever they start us off with this, we can skip everything I just wrote down here and go directly to this equation right here. Okay, these things basically go hand in hand. And so a lot of times in calculus, they'll start you out with this, and they're hoping that you will just write this down and not try to solve everything from there. So we're going to try a couple here before we're done with our video. So this first example, we know that dy dx equals 5 times y. It's going to go through the point 0, 20, or the original equation will. And then right next to it, I just wrote down what we learned on the last slide there. So right away, if I see that dy dx equals 5 times y, kind of written this way, k is 5, I can now start writing out my equation like this. So I'm going to have the initial value. Well, luckily, they gave me the initial value right there. The initial value is 20. So right away I can just say that the function is going to be y equals 20 times e to the k, which was 5x. And now I can use that equation however I want to for the rest of the question. It can be that simple. You don't have to go through all the mess of the last slide. It's already done for you. You just need to make that connection. Okay, this one will be a little bit more challenging. Now we have dy dx equals 2 times y. It goes through the point 1, 14. And again, we have the same relationship here. Once you realize that it's dy dx equals a number times y, we can right away assume that the original equation will be in this form. So for this one, 2y, k is 2. So I'm going to start out by saying y could equal y sub 0 e to the 2x. This time I don't know what the initial value is because the point they give me is 1, 14. But what I can do in situations like this is once I make the connection of this initial step, I can go ahead and plug a 14 in for y and a 1 in for x, and I can just work backwards and solve for the initial value. So in the end for this I would have 14 over, and 2 times 1 is 2 obviously. So I'm going to have e squared underneath. That's going to equal my initial value. And if I went through and did that on my calculator, I should get about 1.895. So that is rounded. Obviously it's not an exact value, but I would get something like that. And so now I could go and say I've solved for this initial value right here. And my overall equation would be y equals 1.895 times an e to the 2x. And that would be the equation that I would get knowing this initial information. Okay, that's where we're going to stop here. We'll practice a few of these in class tomorrow. Jot down any questions you might have.